Hello again. Welcome to the second part of the lesson 1 of our General Physics 2 subject. Today we will discuss the Coulombs Law and we will calculate sample problems. We have learned from the previous discussion about the fundamental rule about the electrical force and charge. So we have learned that like charges repel, meaning if we have two positive sign and we also have two negative sign, they will repel, and if we have positive and negative sign, they will attract. Also, we have learned that an object that has an equal numbers of electrons and protons is considered as electrically charged. The electrical force between any two objects obeys a similar inverse square relationship with distance. So here, this is the inverse square relationship. R here is the distance. Okay? The relationship among electrical force, the charge, and the distance can be stated through Coulombs law. Coulombs law was discovered by the French physicist Charles Coulomb in the 18th century, and it states that for charged particles or objects that are small compared with the distance between them, we can measure the force between these charges, which varies directly as the product of these charges and inversely as the square of the distance between them. Meaning the electrical force can be obtained between these two charges, and it depends on the square of the distance between them. So we will tackle this later. So if you recall the Newton's law of gravitation, so it states that the gravitational force between two objects of mass m1 and m2 is proportional to the product of these masses and inversely proportional to the square of the distance between them. So Coulomb's law is like Newton's law of gravity, but unlike gravity, electric forces can be attractive or repulsive. To further elaborate the Coulomb's law, we can write the Coulomb's law as F equals K times Q1 times Q2 over D squared, where D is the distance between the charged particles, Q1 represents the quantity of charge of one particle, Q2 is the quantity of charge of the other particle, and K is the proportionality constant, where K is equivalent to 9 times 10 to the 9 Newton times meter squared per Coulomb squared. The SI unit of charge is Coulomb. A charge of 1 Coulomb is the charge of 6.24 times 10 to the 18 electrons. So just imagine that a Coulomb represents the amount of charge that passes through a common 100-watt light bulb in about 1 second. So say for instance, if we have a pair of charges of 1 Coulomb each, where it has a 1 meter apart, the force of the repulsion between the two charges would be 9 billion newtons. So imagine that would be more than 10 times the weight of a battleship. Now let us compare the two. We have the Newton's law of gravitation, which is similar to Coulomb's law for electrical charges. However, the difference between the two is that the constant G here is a small magnitude constant, and K here is large magnitude. And also the difference is that the gravitational force is only attractive, while the Coulomb's law can be attractive or repulsive. Okay, but they are both inverse square laws. So meaning if we have a pair of 1 kilogram mass, this is a very small or extremely small compared to a pair of 1 Coulomb charges, which is extremely large. Okay, so again, the greatest difference between these two is that gravity only attracts, but electrical forces may attract or repel. Let us tackle the mathematical form of Coulomb's law. So here, the electrical force is equal to K times Q1, Q2 over R squared, where K here is also equivalent to 1 over 4 pi epsilon naught. And this is a constant that is equal to 9 times 10 to the 9. Okay, so take note here the absolute value bar. Okay, so it is used because the charges Q1 and Q2 can be either positive or negative. So if you remember from your physics 1, the magnitude of force is always positive. But also you have learned in your physics 1 that force is a vector quantity, meaning it has a direction. Okay? So the direction of the force the two charges exert on each other are always along the line joining them. Okay, so if we have charge Q1 and Q2 which have the same sign, or either it have both positive or both negative, the force are repulsive. Okay, so Q1 meaning the force 2 on 1, the charge 1 will go at this direction, and the force 1 on 2, meaning the charge 2 will go to this direction because they will repel from each other. And if the charges have opposite sign, the forces are attractive. Okay, so here the force 2 on 1, meaning the charge 1 will attract to Q2, and here the force 1 on 2, the Q2 here will attract to Q1. So the charges of opposite sign attracts. So the two forces obey Newton's third law. They are always equal in magnitude and opposite in direction, even when the charges are not equal in magnitude. This time, you are going to calculate a sample problem, and this is about force between two charges. Our problem is 2-point charges Q1 is equal to positive 25 nanocoulomb and Q2 is equal to negative 75 nanocoulomb, are separated by a distance r equal to 3 centimeter. Find the magnitude and direction of the electric force, A, force that Q1 exerts on Q2, and B, the force that Q2 exerts on Q1. So here is the illustration of the problem. So the given is the charge 1 is equivalent to 25 nanocoulombs, and that is equal to 25 times 10 to the negative 9 coulomb. Charge 2 is equal to negative 75 nanocoulomb, and that is equal to negative 75 times 10 to the negative 9 coulomb. And our distance r is equivalent to 3 centimeter. And since centimeter is not yet in as a unit, so we need to convert centimeter into meters. So in 1 meter, we have 100 centimeter, and 3 centimeter is equal to 0.03 meters. We need to solve for the force of charge 1 on charge 2 and force on charge 2 exerted on Q1. So force is given by 1 over 4 pi epsilon naught Q1 times Q2 over R squared, and the absolute value bar here means that we are calculating for the magnitude of the force. So 1 over 4 pi epsilon naught is given by 9 times 10 to the 9 Newton meter squared per Coulomb squared. Q1 is equivalent to positive 25 times 10 to the negative 9 coulomb, and Q2 is equivalent to negative 75 times 10 to the negative 9 coulomb. And our R is 0.03 meters. So the magnitude of our force is equal to 0.019 Newton. So since force is a vector quantity and we already have or we already calculated its magnitude, we need to find its direction. So we have positive and negative charge. So meaning they will attract. So the force of charge 1 exerts on charge 2. So this is charge 1 and charge 2. So force of charge 1 on charge 2 is going to the negative direction, and the force of charge 2 exerts on charge 1 is going to the positive direction. And since we have the same values of charges and distance, we can say that the magnitude of force of 1 on 2 is just equal to force of 2 on 1. However, they have opposite direction because of the attractive force. Another sample problem about vector addition of electric forces on a line. So our problem is 2-point charges are located on the x-axis of a coordinate system. So Q1 is equal to 1 nanocoulomb located at x at positive 2 centimeter, and charge 2 is equal to negative 3 nanocoulomb and located at x at positive 4 centimeter. What is the total electric force exerted by Q1 and Q2 on a charge Q3 that is 5 nanocoulomb located at x is equal to 0 or the origin? So the given is charge 1 is 1 nanocoulomb that is equal to 1 times 10 to the negative 9 coulomb at x positive 2 centimeter. So again, this is not in as a unit. We need to convert this, and this is equivalent to 0.02 meters. Charge 2 is equal to negative 3 nanocoulomb, and that is equal to negative 3 times 10 to the negative 9 coulomb located at x at positive 4 centimeter. And this is equivalent to 0.04 meters. So our charge 3 is 5 nanocoulomb, and this is equivalent to 5 times 10 to the negative 9 coulomb located at the origin. So we need to draw the FBD or the free body diagram. So we have the y-axis and x-axis, and here we have a charge 3 at the origin, and the at x at positive 2 centimeter, we have the Q1. At x at 4 centimeter, we have the negative Q2. Okay, so this is the FDD of the problem. Again, we have the charge 3, we have the charge 1 at 2 centimeter, we have the negative charge 2 at 4 centimeter. So the force that Q1 that exerts on Q3 is given by 1 over 4 pi epsilon naught Q1 times Q3 over R13 squared, meaning this is the distance between the charge Q3 and charge Q1. So 1 over 4 pi epsilon naught is equal to 9 times 10 to the 9. Q1 is 1 times 10 to the negative 9. Q3 is 5 times 10 to the negative 9. And the distance between the two is 0.02 meters. So the force that Q1 exerts on 3 is equivalent to 1.12 times 10 to the negative 4 Newton. So here we are going to, since this is only the magnitude, so we need to know the direction of the force. So we have positive Q3 and we also have positive Q1, meaning they will repel. So the force that Q1 exerts on 3 is going to the negative direction. Here, so if we draw this one, okay? So for illustration, so Q3 goes here at negative x direction, okay? So to continue, the positive charge 3 and negative Q2 will attract. So meaning the force of charge 2 on 3 will go to positive direction. And since here the vector quantity of the force of charge 1 on 3 is equivalent to negative 1.12 times 10 to the negative 4 Newton. Again, this is only the magnitude and this one is the vector quantity of the force. So for the force of charge 2 exerted on 3 is equal to 1 over 4 pi epsilon naught times Q2 times Q3 over R2 3 squared. So again, this is 9 times 10 to the 9, and Q2 is equivalent to negative 3 times 10 to the negative 9. Q3 is 5 times 10 to the negative 9, and the distance between Q3 and 2 is 4 centimeters or 0.04 meters. So the magnitude of the force is equivalent to 84 micronewton. And again, the direction is going to the positive x direction. So we can say that the vector of the force of charge 2 exerted on 3 is positive 84 micronewton. And since we need to know the total electric force, so the net force is given by F, that is F3. So we need to add the force of 1 on 3 plus the force 2 on 3. And that is equal to, we need converting this into micronewton. So this is equivalent to negative 112 micronewton plus 84 micronewton. Again, this one from your physics 1, this is a unit vector along x. So our net force is equivalent to negative 28 micronewton along x. For our last sample problem, we are going to solve a vector addition of electric forces in a plane. Our problem is two equal positive charges, Q1, which is equal to Q2, and this is equivalent to 2 microcoulomb, are located at x is equal to 0 and y is equal to 0.3 meters, and x is equal to 0 and y is equal to negative 0.3 meters respectively. What are the magnitude and direction of the total electric force that Q1 and Q2 exert on the third charge Q, which is equal to 4 microcoulomb at x is equal to 0.4, 40 meters, and y is equal to 0. So our given is Q1, we have 2 microcoulomb, and that is equal to 2 times 10 to the negative 6 coulomb, located at x is equal to 0 and y is 0.3 meters. We also have Q2, which is also equivalent to 2 microcoulomb. That is 2 times 10 to the negative 6 coulomb, located at x is equal to 0, and dy is negative 0.3 meters. So we need to find the magnitude of the force, of the total force that Q1 and Q2 exerts on the third charge Q. So we need to find the total F, that is 1 on Q and 2 on Q, where Q is equivalent to 4 microcoulomb. So that is 4 times 10 to the negative 6, located at x is 0.40 meters and y is 0. So again, we need to illustrate this through free body diagram. So drawing the x and y axis, and here we have the Q1, which is located at x is equal to 0. This is the origin. And y is 0.3 meters. And our Q2 is located at negative 3 meters along y, and your x is 0. And your third charge, that is your Q, is located at x is equal to 0.4 meters, and your y is 0. So this is our free body diagram. Okay? And since our charges are all positive, okay? So the interaction between Q1 and the third charge, since they are both positive, they will repel. So our force that is the charge 1 exerted on Q will go here, this one will go down, and the force of charge 2 on Q will go in this direction. Okay, so since we are dealing with vectors, again, this vector here has x and y component. So the x component of this vector is here, and the y component is here. So we have positive x and negative y. For the force 2 on Q, so this is the vector, right? So it has a component of positive x and positive y. Okay. So by looking at this free body diagram, and since the given the charges have similar magnitude, so we can say that the total force of these two, so if you add these two, the x component will add up, or it will double, and the y component of the force will cancel out since they have opposite direction. So let's check. Okay, so the force um of the charged one exerted on Q is equal to the force of charge 2 exerted on Q. And that is equal to 1 over 4 pi epsilon naught. So our charge 1 is 2 microcoulomb. That is 2 times 10 to the negative 6. And our Q is 4 times 10 to the negative 6 coulomb. And the distance between them. Okay? So we need to recall our trigo. So since this side is given, we have 0.3 and this one is 0.4. So we have a right triangle. So we can calculate this side by using the trigonometric idea or concept. So you have to square the 0.3 meters squared plus 0.4 squared, and you square the square root of this is equal to 0.5 meters. So you need to get the hypotenuse. So I think we do not need to review the trigo anymore since you are already in your physics 2, right? So here, this one is 0.5 meters. So this is the distance between the charge 1 and Q. So this is equivalent with the force of charge 2 on Q. Since charge 2 is, the magnitude of charge 2 is also 2 microcoulomb, and Q is 4 times 10 to the negative 6 coulomb. And the distance between charge 2 and Q is also 0.5 meters. That's why our force of 1 on Q and F2 on Q are just equal. So the magnitude is 0.29 Newton. So that is the magnitude. So we need to recall again the trigonometric functions, that is cosine and sine. So as you recall, cosine theta is the adjacent over the hypotenuse. So if we have the theta here, so the adjacent side of the angle is x, and the hypotenuse is this one, the F1 on Q, right? And for the sine theta, the opposite side is this side, the y component, and the hypotenuse is the this vector, right? So getting the x component, the F1 on Q is this one. This is the hypotenuse, right? Hypotenuse, and 0.29, this one, the 0.29 is the hypotenuse. This is the magnitude that we've obtained here. Okay, so cosine theta is adjacent over hypotenuse. So our adjacent side is 0.4 and our hypotenuse is 0.5 meters. So our F1 on Q is 0.23 Newton, and that is equal to F2 on Q. So our theta here is equal to here, and our theta here is equal to here. So just recall your trigonometry. Okay, for the y component, this is the sine theta since we are going to deal with the y component, right? So 0.29 Newton is equal to 0.3 meters, and the hypotenuse is 0.5. Okay? So this is equal to 0.174 Newton, right? And since the F1 on Qy is going to the negative, this is going to the negative, so we have negative 0.0174, and our F2 on Qy is positive, so our total force along Y is 0. So hence, the total force that is contributing here is along X only. So 0.23 Newton plus 0.23 Newton, this one, as what we have expected earlier. So it just doubled. So our total force is equivalent to 0.46 Newton. Thank you so much for listening, and I hope you learned something today. And don't get overwhelmed by all the calculations that we've discussed earlier. So you just need to practice regularly, and eventually you will grasp the idea and you can master the concept about the electric force. So I will see you again next time.